Bonsoir mesdames, bonsoir messieurs, cher public. Bravo d'être encore une fois si nombreux à ces conférences. Comme d'habitude, je vous rappelle qu'il y a également une salle juste ici en face. Donc ceux qui désirent un siège peuvent aller s'asseoir là-bas. Il y aura également la traduction simultanée, bien qu'aujourd'hui ça sera plus facile pour les francophones puisque Alain Aspect parlera en français. Alors, mon nom est Nicolas Gisin, je suis professeur à l'Université de Genève et c'est moi qui ai le plaisir aujourd'hui d'introduire l'orateur de ce soir. Il s'agit du professeur Alain Aspect, qui est professeur à l'Institut d'optique d'Orsay, professeur à l'École polytechnique de Palaisieux et senior scientist au CNRS, en anglais dans le texte. Il a énormément de titres, il a énormément de prix. J'en citerai juste deux, le prix Wolf, qui est considéré comme venant juste avant le prix Nobel, et la médaille d'or du CNRS, qui dans l'imaginaire français vient à peu près au même niveau que le Nobel. Je ne vais pas vous raconter toute sa vie, mais juste vous raconter comment le jeune Aspect est tombé dans la marmite quantique, un peu comme le jeune Obélix dans la marmite de potions magiques. Tout commence dans les années 1970, enfin 70 ou 50-20, comme vous voulez, quand jusqu'après ses études, Alain décide de partir avec sa femme Annie en Afrique en coopération au Cameroun. Évidemment, il décide de prendre des livres avec lui, dont des livres de physique, mais à l'époque, il existait très peu de bons livres de physique quantique en français. Heureusement, un ami lui procure une copie du Cohen, la Bible de l'époque. Alors, le Cohen, bon, mes étudiants, ils savent ce que c'est, mais le Cohen, c'est deux pavés, c'est un livre, c'est deux livres qui forment un énorme pavé de 1500 pages, toutes pleines de magnifiques équations quantiques. Alors évidemment, le jeune Alain se plonge dans une lecture passionnante et attrape le virus quantique. Ce virus ne le lâchera plus jamais. Quand même précisé, donc le Cohen, c'est un ouvrage rédigé par Claude Cohen-Tanouji, le prix Nobel qui a été mentionné avant-hier, ainsi que par Bernard Dieu et Frank Laloé. C'est, je pense, le premier livre de physique quantique écrit en français dans un formalisme moderne. Voilà, après 3 ans d'Afrique et avec le virus quantique, Alain Aspect décide de retourner en France. Maintenant, il sait ce qu'il veut faire, il sait qu'il veut faire de la recherche. Le professeur Humbert, directeur du labo qu'il a accueilli, lui donne à lire un petit papier d'un certain John Bell. Et là, c'est le coup de foudre. Oui, mesdames et messieurs, on peut tomber amoureux d'une idée, surtout d'une idée quantique. C'est ça qu'Alain fera pour sa thèse. Et ça, je vais laisser Alain vous raconter cette aventure magnifique. Mais auparavant, encore 2 points. Premièrement, après avoir lu le papier de Bell, Alain va lui rendre visite. John Bell était à Genève, au CERN, comme ça a déjà été mentionné. Et c'était déjà une célébrité, un grand monsieur. Et le jeune Aspect lui présente son projet. John Bell l'écoute, certainement poliment, avec son sourire. Et ensuite lui pose une question. Avez-vous un poste permanent? En effet, à cette époque, étudier les inégalités de Bell n'était pas du tout à la mode, et l'expérience si difficile, l'expérience que se proposait de réaliser Alain, si difficile qu'on ne pouvait garantir un résultat. Aujourd'hui, c'est typiquement le genre de problème qu'on ne peut pas donner à un thésard, parce qu'un thésard doit, en 3 ans, avoir réalisé un projet original. Or, si c'est original, on ne peut pas garantir que ça finit en 3 ans. Mais bon, à l'époque, à cette époque lointaine, peut-être pas lointaine dans le temps, mais certainement lointaine dans l'esprit du temps, on pouvait avoir un poste permanent, même sans avoir de thèse. Et Alain Aspect avait un tel poste permanent. Donc, il a pu se lancer dans cette aventure. Juste encore une dernière chose, un avertissement. Le virus quantique est contagieux. Et je me dois quand même de vous avertir qu'il n'existe pas d'antidote.
Merci beaucoup Nicolas pour cette introduction magnifique. Le problème avec les coups de foudre, c'est que parfois on peut être plusieurs à partager un coup de foudre pour le même objet. Et j'ai découvert un jour que Nicolas utilisait la même expression que moi. Il est lui aussi tombé amoureux. Il a lui aussi eu le coup de foudre pour le papier de John Bell. Ça fait partie des nombreux plaisirs que nous partageons. Donc, je vais vous raconter une longue histoire qui commence en 1935 avec Einstein et qui se poursuit aujourd'hui avec ce que nous sommes un certain nombre à appeler une nouvelle révolution quantique. Et pour ceux qui veulent en savoir un petit peu plus, en anglais, j'ai d'une part un texte que l'on peut télécharger sur le web, d'autre part un texte qui est la préface des œuvres de John Bell sur les fondements de la physique quantique.
Bell's writings on the basics of quantum physics. I recommend you buy it, not just for the preface, but simply because John Bell's papers are all marvelous. At the same time, you'll also be able to read the preface, which develops some of the ideas which I'll be sharing with you today. And if you want to know more about not just quantum physics, but learn more about some other aspects of modern physics, then why not buy the latest edition of this book? It was published in 2005 by Odile Jacob. There are about 12 authors who've written on various subjects of modern physics in this book. It's for an informed but general public, and I think it's something which you should have on your bookshelf if you're interested in science. Today I'm going to take you back to, well, you see, to make the interpreter's life easier and to ensure that the English speakers among us can follow my presentation more readily. I'm going to give you the transparencies, the slides in English, and my talk will be in French. We're going to go back to what's known as the Einstein-Podolsky-Rosen problem, and I'm going to discuss the way in which John Bell developed the problems discussed by Einstein, Podolsky, and Rosen. They had taken this to a point, or he took it to a point which the authors probably never suspected would be possible, which led to the experimental tests of Bell's inequalities. And in the last part of my talk, I shall be looking at how all this leads to quantum information and what could probably be termed a new quantum revolution. So in the first part of my talk, I'm going to talk about Einstein, Podolsky, and Rosen. EPR. We all know that Einstein had a rather strange attitude towards quantum physics. There's no doubt about the fact that he was one of the most famous founding fathers of quantum physics. C. Planck talked about the exchange of energy between rays and matter in 1900. In 1905, Einstein was even more radical. Not only did exchanges happen through quanta, Lichtquanten, light itself is also quantified. It's not just the exchange. The light itself is made up of grains, which subsequently were determined to be photons. From his hypothesis, Einstein draws a number of consequences, and more specifically as to what one should observe in the photoelectric effect. It will take a good 10 years more for physicists to really take on board the validity of Einstein's theory. At first, no one took him seriously. Midical, the great Midical, conducted some tests and realized that these measures helped to prove that Einstein's theory was wrong. He was an excellent experimentalist, and having conducted his experiments, he found that Einstein was right. And don't forget, Einstein's Nobel Prize was for photoelectric effect and not the theory of relativity. At the beginning of quantum physics, in the very early days of quantum physics, Einstein moved away from the main trend prevailing at the time, which was being developed by Niels Bohr in Copenhagen mainly. He deviated from the way in which Bohr and his pupils interpreted mathematical formalism. Since the beginning of this week, you've heard all of us say that we all agree on equations and mathematical formalism, but this formalism is so far away from the everyday world that to interpret equations is a real problem. It's a real issue. And the most current interpretation was developed by Niels Bohr and his followers, the Copenhagen interpretation, and Einstein increasingly disagreed with this interpretation by Bohr, and he raised a number of objections. There was the Solvay Congress, where every day Einstein raised an objection, and the next day Niels Bohr responded to that objection. A few years after the Solvay Congress, Einstein raised an objection which I think we can safely say is still around today, and it was presented in this paper, on this article. It's the Einstein-Podolsky-Rosen paper. That's what it's known as. And in this paper, Einstein and his colleagues for the first time discovered that quantum formalism, this mathematical formalism, made it possible to envisage so-called pairs of entangled particles. And at the same time, Schrödinger, one of the founding fathers of quantum physics, he was also a little bit outside the Copenhagen school, where Schrödinger also discovered entanglement, which led him to present a peculiar object, which we'll discuss later on, Schrödinger's cat. But it was Einstein, Podolsky, and Rosen's objection, which ultimately, in the long term, turned out to have the greatest consequences, and that's what we're going to be discussing today. This paper, Einstein, Podolsky, and Rosen's article, met with very little response when it was published. Most physicists underestimated it, and it took Bell's work 30 years later, after Rosen and Einstein's death, to shed some more light on the theory which they developed in their article. That's what I'm going to be developing here, and then at the end I'll explain how this entanglement finds itself right at the core of what we today call quantum information. So what is the issue? What was the problem that obsessed Einstein? Einstein was very unhappy that formalism of quantum physics made probabilistic predictions, statistical predictions. In quantum physics, most of the time you say, I'm preparing a system in this way, then I measure such a quantity, and what mathematics tell me is that when I measure this quantity, I have 23% of observing result 1, 47% observing result number 2, and if I haven't gone wrong somewhere, then 30% to observe result number 3. And Einstein simply could not accept that a fundamental theory was a theory which expressed its results in terms of probabilities. He knew that many physical theories were expressed in terms of probability. For instance, if you want to describe the distribution of velocity of molecules in the atmosphere here, you will be using a distribution, a Maxwell-Boltzmann distribution probability. That's a useful tool. Nobody doubts the fact that each molecule has its own determined velocity, but if you wanted to describe each one, it would be impossible. There are too many molecules in principle. However, you could describe the velocity of each molecule. So probability is a handy tool, but it's not the ultimate answer to describing molecules in this room. Einstein felt that the fact that quantum physics only made probabilistic predictions meant that there had to be a more accurate description, and this I have symbolized here by showing you a Swiss watch, the mechanism of a Swiss watch. There had to be something more detailed. You just don't, the hands is not all there is to a watch. There's more to it, to the movement. And it was felt that if there was such a level of detail, subquantic detail, then in 1935, he felt he had been able to demonstrate that it was crucial that such a level of detail had to be found, otherwise the theory was meaningless. Bohr strongly opposed Einstein's conclusion, and once again, it wasn't until Bell and his theorem, that's 30 years later, that it was possible to take the debate forward. It was a magnificent debate, but very little progress was made over 30 years until Bell arrived. So what is it? This is Einstein-Podolsky-Rosen's experiment as carried out in its modern form. I'll be describing it to you whilst scrupulously respecting Einstein, Podolsky, and Rosen's argument. We're going to have a pair of photons, one photon going to the left and one going to the right. They've got different colors, so you can identify the two different photons. And we're going to measure polarization on each of these photons. What's the polarization of light? It's the fact that when you have a light beam being propagated, you have an electric field which vibrates perpendicular to the direction of propagation, and it can vibrate in a plane which can have any orientation. That's what polarization means. If I have a light beam, say a laser beam, moving over to the left, and I put a polarizer which is oriented in direction little a, say, what happens? If the light beam is polarized according to A, the light will emerge in an ordinary ray, and we get the result +1. But if the light beam which comes here is perpendicularly polarized, perpendicular to the polarizer measuring, it'll come out in the second channel, which we'll call channel -1. If the light is polarized at an angle to direction A, then a fraction will go upwards and a fraction of the light is going to be deflected downwards. For instance, if the polarization is at 45 degrees of A, 50% of the light will go up and 50% will go down. If it's at 30 degrees, a 30-degree angle, 3/4 will go up, 1/4 will go down, etc. So if you have a big light beam, there's no mystery here. If you have one photon, only one photon, that photon can't be cut into two. So for instance, if you send a photon which is polarized at 45, an angle of 45 to the polarizing direction, in one case out of two, it'll go up, and in one case of two, it'll go down. That is the probabilistic aspect of quantum physics prediction. You get a probabilistic result. This experiment can be carried out many times over. You send these pairs of photons out, you emit them, and you can work out single probabilities, +2a, when the polarizer is oriented according to A, P minus B, the probability is to get -1 when the second polarizer is oriented according to letter B. That's not so interesting, but what is fascinating is to take a look at what we call joint probabilities. For example, P plus plus AB, what's that? That's the probability of getting +1 here and +1 there for the same pair of photons when the polarizers are oriented according to A and B. You can measure these 4 probabilities. For the time being, this is not quantum physics, except for the fact that we're dealing with photons. Well, the EPR situation is going to kick in as soon as we are able to prepare the 2 photons in this polarizing state here. I can see some of you grimacing. You were told that this was physics for the general public. I never promised that I wouldn't be showing any slides with equations. Some people do. I never promised that. But please don't panic because you can see equations here. Don't let that frighten you. I'm sure many of you have been to concerts, and some people who go to concerts bring the score along and they look at the notes while the orchestra is playing. But many of you just listen to the music. I certainly only listen to the music. I don't read the score. So if you don't know how to read equations, then just listen to me. I'm not going to sing. Don't worry. I'm not going to start singing. Just listen to the music of my words. And those of you who know how to read equations, be my guest. Go ahead. I don't want to frustrate you. You're very welcome to read them. So, for instance, I'm going to try and tell you the music that emerges from this score here. this entangled state. This is the entangled EPR state. The first term here, XX, designates a pair of photons, both of which are polarized in direction X. You have the axis here. So if I have a pair of photons, both of which are polarized in direction X, I will designate them by XX. If I have a pair of photons, both of which are polarized according to the Y-axis, I call them YY. Mathematically, what Einstein, Podolsky, and Rosen have noticed was that the formalism of quantum mechanics make it possible to consider superposition of XX and YY. That's possible, and that is disturbing. May not disturb you, but if I tell you that it's just as disturbing as to consider that a cat is both dead and alive at the same time, you'll understand why a moment ago I said that Schrödinger came up with an analogous situation at almost the same time. So it's a bit disturbing to have a pair which is both XX and YY. We've heard of situations like that this week. You've been told, for example, that you could have electrical current which both moves in one direction and in the other direction, all at the same time. Well, this situation here is just as much of a paradox. Why is it a paradox? Well, you might say, I don't see why this is a paradox. Is it a paradox? Well, I'll show you why. When you have an equation, yes, thank you for moving those flowers. Why don't you just put them down on the floor, because they really get in the way, those flowers. Thank you. I'm sorry. I do apologize to the kind people who put those flowers there, but they are a little bit in the way. Right, so when you have the quantum state described in this equation here, once you have that state, quantum mathematics will enable you to calculate the various probabilities I mentioned a moment ago. For instance, if you calculate simple probabilities, you'll have the result, this result, P plus equals P minus equals 50% regardless of orientation. Regardless of orientation, 50% of chance of going one way, 50% of chance of going the other way. Those of you who know about this will know that light, in this case, will be totally unpolarized, and the same on the other side. When you calculate joint probabilities, here something actually happens, because P plus plus or P minus minus have the value, this is what quantum physics tell us, the state of half of the square of the cosine between the angle of the two polarizers. You take angle 0, both polarizers are pointing in the same direction, you'll find that P plus plus equals a half. And I'm telling you that this is very surprising. It's a very strong correlation. You can't see with the naked eye that you have a very strong correlation here, but let me show you that it really is so. I'm going to convince him. P plus 2a, the likelihood of this happening is 50%, and I tell you that the joint probability of getting this result and that result is also 50%, which means that the probability, the conditional probability of obtaining this result here when I've already achieved this first result, that conditional probability is 100%. In other terms, we find ourselves in the following situation. Here we have 50% likelihood of having +1 and 50% chance of having -1. If you flip a coin, it can be either heads or tails. The same on the other side. It can be either heads or tails. But if I have +1 here, I'm sure that I'll get +1 on the other end. And with -1 on the left, I'm sure that I'll also get -1 on the right. That's what we call a very strong correlation. It may seem random. It is random on one side and it's random on the other. If I have heads on one side, I'll have heads on the other, and tails on one side, it'll also be tails on the other. A very strong correlation. Let me share a small technical point with you. One has, in quantitative terms, to determine the coefficient. It's the average value, the probability of getting an identical results, plus, plus, minus, minus, minus the likelihood of getting crossed results, plus, minus, minus, plus. This is a conventional definition, a classical definition, the coefficient. And if into this I feed the results of the quantum results for P++, I will get a result which is that this correlation coefficient for cosine 2 times the angle. It's not very exciting, but we're going to need this later on. What matters is that you can check that if AB angle is 0, the correlation coefficient is 1. So for the two parallel polarizers, there will be 100% correlation under quantum physics. in terms of quantum physics. And this is when it becomes interesting. The fact that we have strong, very strong correlations between distant results or results at a distance, that you don't have to get too excited about it and say it's a mystery, it's a miracle, etc. But it is an important fact, and we need to understand it. I decided to go in for physics before I even caught the virus that Nicolas mentioned a moment ago. I decided that I liked physics because when there were correlations between different events across the world, there was a cause for these correlations. We need to understand why events occur sequentially and in an ordered fashion and are not completely random. And once we have a strong correlation between something that happens at this end and something else that happens at that end, then obviously you want to try and understand the cause. You can always say, of course, that it's easy. I've done a quantum calculation. Just look at the equations. That's one way, of course, of understanding the phenomenon. But unlike some of my colleagues, distinguished theorists, and some of them are sitting right here today, to just look at equations, stare them in the eye, is not, to me, a wholly satisfactory explanation. I like to have intuitive models. I like an image, a simple model, to intuitively understand these correlations. Of course, you have to have quantitative calculations. You need equations. But before you actually get down to the equations, I like to have a simple model. So we're going to conduct an experiment, a great experiment, and we can do it all of us together. It's very straightforward. We have the left-hand side of the room and the right-hand side of the room. And those of you over there, you're quite far away from the people sitting in the other half of the room. And look at the screen very carefully, and then we'll see if there isn't a correlation between what you can see at one side of the screen of the room and the others. We'll count 1, 2, 3. What did you see up there? Go ahead. You saw a little green dot going round. What did you see? You didn't see anything at all. Yeah? Okay. Right. Thierry Gemarchi, although he's a theorist and not an experimentalist, in spite of all that, he saw a little green dot going round and round. So we had a strong correlation between what you saw and what these guys here saw. We have a simple model. This little laser pointer sent the dot onto the screen, the light spread to the room, and everybody could see it. That's what I call a simple model. It's easy to understand. You're not going to start shouting, hey, it's a miracle. There's just a strong correlation, and we have a simple model to illustrate the strong correlation. So that's basically what we're looking for. Now, if you're looking for a simple image, the most basic, the simplest way for a quantum physicist to carry out a calculation, you'd be hard put to find a model, an image, which is as simple as the one I've just described. Why? Well, because quantum calculations are carried out in an abstract space, in a space which describes two particles at the same time, the one that goes left and the one that goes right. It's the time-space zone. And because this calculation is carried out with strange objects which live in a time-space which is not our real space, that's why it's impossible to produce as simple an image as the one I just described to you to illustrate my little green laser pointer. And the reason why we can't produce a simple image is that mathematically it's not possible to factor the quantity which is described here. If we could write it as a term which is associated to the first photon and a term associated with the second photon, we could then say the first photon has a polarization like this and the second photon has a polarization like that. But since it's not possible to factor the fact that it's both this and that all at the same time, that's what makes it so difficult.
So we need to press further. And many theorists have also come up with these explanations. Jacques Perez, for instance, emphasized that quantum phenomena do not occur in a Hilbert space. They occur in a laboratory, which is a real place. So we shouldn't be discouraged. We have to try and come up with a description in a real space. And there is a way of doing it. use a more complicated calculation method than the one I showed you earlier on. We're going to first measure at the first polarizer and then measure at the second polarizer, because the first polarizer is perhaps closer to the source, or the photon was introduced first. So if that's what we do, we then get the same result. We've got 50% probability of getting +1 and 50% probability of getting -1. So this is confirmed, and we either get +1 or -1. Then what do? Then I take my Bible, as Nicholas called it for French speakers, Cohen Danuji's book, and we look what's in it. And you have the famous postulate of the reduction of the packet of waves. So just after measurement, you have the collapse of the state vector, a projection onto the eigenspace associated to the result. So this is what it looks like. If I've got +1, this projection on the eigenspace associated to the result when I get +1, which matches the results of the measurements of the polarization of the photon in this direction, just after having taken the measurement, this projection gives me a pair of photons, and both of them are going to be polarized this way. But if I get -1, this projection tells me that just after measurement I've got a pair of photons. They are polarized perpendicularly towards the lower part of the plane. And that's what you can find in the Bible. Once this is done, I then look at what's happening at the second polarizer. Now, if I get +1, I have this state here, and now I have this state here. If I place the polarizer in the direction that is parallel to A, the second polarizer is polarized according to direction A, and again I get the same pair of photons. If I look at the other result, which matches this prediction here, or this projection here, the second photon has been polarized perpendicularly to A, so again they're here. So I'm back to the results which had been arrived at using a more elegant equation, which I couldn't get to in the real space. So it's not difficult to show that if the second polarizer is orientated in a certain way, you get the same results. So now we have a very simple image which is clearly understood and which is in our space, the space that we live in, the three-dimensional space that we live in. There's only one slight hitch. If we get +1, the pair of photons is polarized in parallel to A, but if we've got -1 here, then the polarized pair is at -A. So the measurement result that you get here, which appears to be random, depending on whether you get the first or the second result, it would seem that the second photon instantly is either going to put itself in a parallel position to A or in a perpendicular position to A, and this instantly, whatever the distance between the two sides. And obviously this is unacceptable. This was unacceptable to Einstein. Let's not forget that Einstein started off in life by stating the theory of relativity. And one of the most important results of this relativity is that nothing exceeds the speed of light. Now here, if I get +1 here, instantly the photons are +A, and if I get -1, the other photon is polarized perpendicularly to A. This is totally unacceptable to Einstein. And so Einstein then wondered whether it was possible to explain these correlations differently. And the obvious response is yes, of course, you can use something like my green point. Let's say that from the very beginning, when the two photons are emitted, they are at the same polarization. From the beginning, they are both polarized according to X. So obviously, they're going to be +1. And then the second pair, perhaps, the two are going to be polarized according to the y-axis. Then, obviously, it'll come as no surprise that they come out at -1. And you can generalize this. And if you take it that from the beginning, the pair of photons share common properties, and it's the same property which is brought by one photon on this side and by the other photon on this other side, which is going to determine the measurements, then you can come to the correlations and understand them. So you have a simple and convincing image, which is the analog of the one you develop when you have real twins that, in fact, fall ill at the same time and for the same reason, simply because the two twins have the same chromosomes, identical chromosomes. And if you would say that, nobody would quibble. This is the same case here. From the very beginning, we accept that both photons have identical chromosomes. So this amounts to completing quantum formalism, because in quantum formalism all the pairs are described by the famous vector that I didn't describe here. They're all described, all the pairs are described using the same mathematical quantum object, whereas here I'm talking about these pairs that this way, these ones that way, etc. So I've introduced different pairs from the very beginning. So I'm completing quantum formalism, and obviously Einstein was very happy with this turn of events, because the only reasonable model that I'm familiar with to explain these correlations, I accept that this is the way to go, and therefore I conclude that we need to complete quantum formalism. Niels Bohr did not agree with that at all. And Bohr made it his business to state that if we were to complete quantum formalism, then it would just be destroyed. And we'll see later on that he was most likely right in saying that. But he didn't really explain it properly. But you shouldn't be too angry with him, because he developed something which is called complementarity. Complementarity is as follows: if you do something properly, then you have to pay the price for that by doing something else which not properly. And Bohr said in particular that equity and clarity are complementary variables, and Bohr made it his business to state things as clearly as possible. So when you read Niels Bohr, you see that you didn't agree, but you can read him time and time again. It nevertheless is very difficult to understand what he was about. So what happened next? Well, Bohr and Einstein went on discussing the problem throughout their life. This is them in Princeton. At a time, it wasn't politically incorrect to be pictured as smoking, and I must say that most physicists, in fact, were not at all interested in this debate. They wrote a lot of papers. Nobody was interested in the ongoing debate. Now, why was this? Not because people were particularly dull-witted, but they were two old men discussing quantum physics, and the young people every day use quantum mechanics to make extraordinary discoveries. Quantum mechanics allowed us to make all sorts of extraordinary discoveries in the 20s and 30s and 40s. Extraordinary results were obtained. We started to understand nature. You've heard it said several times this week that you can only understand the stability of matter by resorting to quantum physics. Classical physics doesn't allow you to understand the structure and properties of matter. Once that was done, you could understand how light was absorbed or emitted by matter. Then there's the theory allowing us to describe atoms, molecules, spontaneous emission, solid properties, as well as very strange phenomena, superconductivity, which is what we discussed the first evening, superfluidity, and even elementary particles. As we went on discovering elementary particles, quantum physics obviously is the right frame to discover these matters. And then we made extraordinary inventions and transistors, lasers, etc. So extraordinary results were achieved. And people were well aware, well, there are not that many people who were interested in the ongoing debate, but those who were interested in the ongoing debate between Bohr and Einstein had realized that there was no disagreement between Bohr and Einstein as to the result of the calculations, the way of doing the calculations, of using the equations. Nobody found fault with that. The only problem that they didn't agree on was the interpreting the underlying epistemology, and young people who are far more pragmatic weren't really interested in the debate and used quantum formalism. And then came along John Bell. As was explained, he was a theorist who worked at CERN and who obtained extraordinary, remarkable results in the physics of particles. And he was also obsessed by the interpretation problems of quantum physics. He'd read EPR's article, a number of other papers as well, and he thought a great deal about these matters, and at the end of the day decided to take Einstein's ideas seriously. Let's introduce a simple model with these ideas, i.e. from the point of emission of these two pairs of photons, we'll agree that they have some properties which we will name lambda. And the most important aspect is that the photon that goes to the left has all the lambda properties, the photon that goes to the right has all the lambda properties, and when they get to the polarizer, this first photon, the result of the measurement is going to be described by a function which depends on the lambda properties and the orientation of the polarizer. And then we'll ask a function to come up with +1 or -1. Same applies to the second polarizer, described by a function which is -1 or +1, and depends on the pair of photons and the lambda properties and the orientation of the polarizers. The properties are not the same all the time, so we have to introduce a notion of distribution of probabilities to see whether we're going to get this lambda or not, with the probability calculation with the positive function, and the sum of all probabilities should be equal to 100%. So, if you come up with this theory, you're going to give specific functions for A, B, and rho, and then you can calculate the correlation coefficient of polarization, which appears in a very simple way in this equation. And for those who can read the music, will understand immediately. So let's take an example, a simple example. If you think about it 5 minutes, you're going to come up with this equation. So the simple example is as follows. When the two photons are emitted, they have the same linear polarization. And then each photon is going to travel towards the polarizer. Then we need a model for what's happening at the polarizer. We need +1 or -1. If it's orientated according to this polarization, then I'll have +1. If it's orientated perpendicularly to the polarizer, then I'm going to get a result which is -1. And as I'm not stupid, I imagine that the limit is at 45 degrees between the two. So if we're at -45% of the direction, we get +1. If it's other 45 degrees, then you'll get -1. So you develop the model. You take it that all the polarizations exist with the same probability. There's invariation by rotation. You develop your model, and you see that this very simple model gives you 100% prediction. Here the 0, a correlation -1 when the two polarizers are crossed, -1 total correlation, but if you have +1 one side, you're going to have -1 the other side. And at 45 degrees, well, there's no correlation, which means that this is totally random, and what is random is non-correlated, and what is remarkable, that is not very different from the prediction of quantum mechanics with the cosine squared of the angle, which gives you the same result as provided for in quantum mechanics. So Einstein's theory was quite correct. So then we again ask our friends who are theorists. They have Bibles, a thick volume with all sorts of formulae and all sorts of functions, all the many functions that you're familiar with. I'm sure you're going to find a function which will be far more subtle and refined than this one. So is there a model that can help us adjust to the quantum predictions for all the angles? So this is what John Bell asked himself. He was a fantastic theorist, and his theorem allows us to answer the question. So please look at the screen carefully, because if you look properly, you'll see Bell's theorem and you'll remember it forever and ever, because it's that. Bell's theorem is no, there is no model, no function, a sophisticated function that would allow you, with this result of a model, to reproduce the quantum predictions for all the angles. So how does it work? This is how it works. So this is the Bell theorem. There are no local hidden variable theory, in the keeping with the spirit of Einstein's ideas, that reproduce quantum mechanical predictions for EPR correlations of all the orientations of polarizers. There's no way you can do away with the differences between the blue and red predictions for all angles. So John Bell can prove that whatever model that you use, without specifying the values for A's, B's and rho's, you can show that there is a quantity S. When it is calculated using this model here, is between -2 and +2. It's a simple algebra calculation, high school algebra calculation. A 16-year-old can calculate this without any problems whatsoever. So what's this S quantity? It combines the correlation coefficients that you've calculated, taking two orientations, A and A plus and A and B plus. So you're going to have A, B, and you'll combine them all. For all these orientations, you're going to calculate the correlation coefficient with the theory, it's a hidden variable theory. And so long as you've got capital A, capital B in rows, and John Bell can show that this quantity S lies obviously between -2 and +2. Now let's take a look at the quantum mechanics prediction cosine 2AB. For those who've done trigonometry know that if I take an angle AB 22 degrees and a half, we've doubled that, 45, and the cosine of 45 is 1 over the square root of 2. So if I take this orientation with 22, 5, 22, 5, 22, 5, here I'm going to have the cosine of 45, 1 square root of 2, AB plus A plus B plus, A 1 over square root of 2, and again we're at 67.5. I double it, so then the cosine is -1 over square root of 2. So again I plus 1 over square root of 2. If I look at all these orientations, A plus, B plus, the prediction of quantum mechanics is that S is equal to 2 divided by the square root of 2, which is 2.8, which is bigger than 2, in contradiction with what you should have if the correlations can be expressed using an Einstein-type model. That's Bell's theorem. So, it's no longer a problem of interpretation, it's a problem of conflict between predictions. And you're going to be able to settle the debate once and for all by carrying out an experiment. Now, obviously, if you come up with something which is in contradiction with quantum mechanics, which has been so successful, you have to take a closer look at this contradiction, because there's no point in fighting windmills. So, let's take a closer look. What needs to be done to achieve these Bell's inequalities? What leads to the conflict with quantum physics? Now, to be in conflict with the inequalities of Bell, you have to try and explain these correlations and saying that the same parameters from the very start, and then the photon brings the lambda parameters or the particles, and the result of measurement will only depend on what's happening here with all the properties and depending on the orientation of the polarizer, which is here. This is what we call a local realistic world view. This is what Einstein was about. If you have a system, it's well defined in the time-space. And if you take a measurement, then the result of the measurement can only depend on the properties that exist here and the way in which you fiddle with the knobs of the measurement apparatus, which is here. So Bell stresses the importance of the condition of locality to express the inequalities of Bell. He also emphasizes that the result A of lambda A, which describes the way in which this apparatus is going to react to the photon characterized by lambda, could only depend on A. It cannot depend on the orientation of the other polarizer, which is far more remote. And if it could, in fact, depend on the orientation of the other, more distant polarizer, then you couldn't demonstrate Bell's inequalities. So there would be a hidden variable theory. So the distribution of probabilities, which describes the way in which the pairs are emitted at source, all depends on the orientations with which you're going to make the measurements. Then you couldn't describe the Bell's inequalities and you'd have a model that does work. So Bell insists on the importance of this condition, locality condition, which is necessary if you want to be in conflict with quantum theory. It's a very reasonable condition. Most experimentalists believe that the result of measurements made here doesn't really depend on the orientation of the polarizer over there. But anyway, anything could be possible. As Bell points out,
faut arriver à la raccrocher. Oui, c'est pas évident, hein? Tu es un expérimentateur, Nicolas. Sinon, j'appelle un théoricien. Hein, ah, voilà le technicien. Je crois qu'on va laisser faire le technicien.
C'est quoi qui croche là?
Je sais pas. Merci. Alors j'ai été. Oula, ça c'est la. Ah non, j'ai eu chaud là.
So let's get back to what we were looking at. So Bell pointed out that if it is possible to change during the photon's time of propagation, change the orientation of the polarizer, then it's obvious, given Einstein's theory, it's obvious that the result of the measurement made here is not going to depend on the orientation of the polarizer over there, because in the meantime change has taken place and there's no time for the signal to get across to state the new value. Again, if I change the orientations once the photons have left the source, it's obvious the way in which I've prepared them in the source cannot depend on the way in which we are going to orientate the polarizers later on. So Bell points out that if you could quickly turn the polarizers around whilst the photons are moving about, then the locality hypothesis would become the consequence of Einstein's relativity theory. So, following on from that, what we understand from Bell's inequalities is that there's a profound conflict between quantum mechanics and Einstein's worldview, which I call local realism, based on relativity. So it's possible to conduct an experiment And what's extraordinary is, despite all the results achieved in quantum physics in 1964, when Bell's paper was published, there were no experimental results available to test Bell's inequalities, because all the experiments that were carried out and it was discovered that all the correlations can be described within classical physics. And we'd had to invent experimental situations which were very peculiar indeed, so as to arrive at situations as what was predicted by quantum physics was explicitly contradictory to Bell's inequalities. And this was proposed by four physicists, CHSH as the initials of these four physicists. And I'm now going to explain this further. Three periods. The heroic pioneers, the experiments which were conducted in optics between 1975 and 1982. No one, in fact, was competing with us in our laboratory. And then in 1988, a number of experiments took place, extraordinary experiments with the modern generation. And I'm going to talk to you about the second and the third period and the second and third series of experiments. The first series of experiments, I'll just touch upon the period. In 1972, we lived in interesting times. Clauser, who was working at Berkeley, came up with a result which was in violation of Bell's inequalities, but Pipkin in Harvard, Berkeley, Harvard, the two rival universities, Pipkin, working at Harvard, came up with a result in keeping with Bell's inequalities and contradictory to quantum physics. Believe it or not, in a few years later, in 1976, someone right in the middle in Texas, people in Texas are not really known for their knowledge of quantum physics. I mean, when you think of a Texan, you think of something else. So at Texas A&M, agricultural and mechanical, so you could think in terms of quantum mechanics, but it wasn't really what they were about. In 1976, Ed Fry came up with another experiment which came up with the same results that Clauser had achieved in keeping with quantum mechanics. Now, if you look at the diagrams of all these experiments, you would understand that these experiments were very different indeed from the diagrams of the experiments that I showed you early on of ideal thought. And the reason why I became interested in 1975, when I became smitten by Bell's papers and theories, I thought it was such a fundamental debate that the experimental diagram should be, or protocol should be, as close as possible to the theory discussed by the theorists, and that was the purpose of the whole work. So the key point was to first develop a source of pairs of entangled photons far more effective than the ones that had been developed in the past. And to achieve that, I was very lucky indeed, because a lot of progress had been achieved in the field of lasers. Lasers had been invented in the 60s, and in 1975 we could use lasers and determine the wavelength of the lasers, and by superimposing two laser photons I could excite a calcium atom here, so the atom had no choice. The only thing it could do could become unexcited by emitting two entangled polarized photons. Why? This was explained earlier on this week, because of the phenomenon of interference. So as to go from excited to unexcited, it can either travel down this path or down this path here. So there was interference, and if you write out the equation properly, you arrive at this result. But I can assure you it's not interference in real space terms, it's interference in the Hilbert space. But in a real laboratory, this is what the laboratory looks like. It's extremely complicated. There are 3 lasers involved, vacuum chambers and all sorts of electronics, but the results were extraordinary, because at the end we were able to detect 100 coincidences by second. So in 100 seconds, you've got 10,000 coincidences. So in statistical terms, the uncertainty, which is the square root of 10,000, you know that that's 100. So an uncertainty of 100 on a result of 10,000 is a precision of 1%. So in a couple of minutes, I could get this kind of precision. Clauser had to do it for about 24 hours to achieve the same degree of accuracy, and it's easier to stabilize an experiment for 2 minutes than for 24 hours.
L'expérience des autres.
So the first thing we did was to repeat others' experiments. So that was fairly far away from the Gedanken experiment, but with one alteration, one amendment, and that was as follows. At that time, there were many people saying, well, entanglement, okay, at a short distance. It's a microscopic phenomenon. Everyone knows that in the helium atom, the two electrons are entangled, and in the helium atom, they're just a nanometer apart, but that's going to disappear if the distance grows. So we said, what do you mean by a large distance? And the theorists started scratching their head and said the coherence length of a photon. Well, the coherence length of a photon was 1 meter 50. So we put the polarizer 6 meters away. We set them at a distance of 6 meters, and we still got entanglement. Even at 6 meters, we continued to be in breach of Bell's inequalities. So I really got to work on the program, making schemes which were closer and closer to the Gedanken experiment. And this was the first diagram, which was very like the EPR Gedanken experiment. I managed to produce a setup because you couldn't buy this. It wasn't available on the market. I was fortunate in having some friends at Philips, and I probably slipped them a foie gras or two just to get them to help me. And they made me separators and polarizers. They manufactured for me, which worked just like in the Gedanken experiment. If the photon is polarized along here, it'll come out here. If it's polarized perpendicularly, it'll go out there. With the previous polarizers, if it was polarized that way, it would go, and if it was perpendicular, it would be lost. The theorists will say, well, it doesn't matter. If you see something, it's +1. If you don't see anything, it means it's -1. Well, but sure, the theorist wasn't completely wrong. You can do something with that, but that's certainly not as good as being able to actually measure the -1. I think that Thierry will be very unhappy that I said that, but there we are. So for the first time ever, we had a polarization analyzer. We had +1 and -1 on both ends. And why is this so fantastic? Well, it's because when you don't get -1, the -1 result, you have to have a very stable source. Otherwise, the results will be meaningless. But with this type of setup, you don't need to worry about the stability of your source, because on one counting, say 100 seconds, you measure plus, plus, minus, plus, plus, minus, minus, plus, minus, and minus, plus. And you have the 4 numbers, then you get this ratio, and you have your polarization correlation coefficient. You don't need any additional calibration. And this is the result we achieved. The S quantity, which is subject to Bell's inequalities, the green curve is a prediction of quantum mechanics, taking into account slight imperfections in our experiment, which were measured a priori, and the red dots are the results of our measurements. All the dots you see here are in violation of Bell inequalities, and the same is true of the points below in the slashed area. With this curve, I can tell you that in most cases you don't violate Bell inequalities, because even if you've produced polarized photons which are correlated and polarized, if you're not familiar with the Bell theorem, you'll say, well, I'm going to measure them at 0 degrees, at 45-degree angle and 80-degree angle. If you do it at 0, you'll get it here. There'll be no difference between quantum prediction and Bell inequalities. 45 degrees, you'll end up here, and there'll be even less difference. And at 80 degrees, you'll come here. You'll come up here. You need the Bell inequalities to know where you should be measuring to find a possible conflict between quantum physics and Bell inequalities. Leave it at that. The guys at CERN, if they had found the X boson with the Higgs boson with that, we say we have 40 error bars here, which is beyond any discussion. This result was obtained in 1982, and it's still a record. It still hadn't been exceeded in 98, and I can assure you we weren't doped. Huh? We were the strongest thing we were on was foie gras. Last diagram, closer and closer to the Gedanken experiment. I was told I could talk for an hour and a quarter. Is that right? So I still have a little bit of time left. Okay? So this is the last diagram. I told you that the dream was to be able to change the orientation of the polarizers while the photons were in flight, moving between the source and the detector. Typically, there were 6 meters. The distance was 6 meters, and it takes light 20 nanoseconds to cover 6 meters. 20 nanoseconds, not a whole lot. A nanosecond is a billionth of a second. So if I show you the setup, the polarizer and the polarization separator, and here photomultipliers. These photomultipliers, we talked about them the other day. Someone asked a question, and I said, yes, cosmic rays. It's not very difficult. You put in LED screens. Well, this thing here weighed 20 kilos here, another 20 kilos of metal work here. You can't move all that, turn it right round in 20 nanoseconds. You know, dream on. What we did put together was a sort of optical switch which either lets the light go straight through or move up. It's like a point on a railway track. So either the light moves straight on or it is deviated to the side. And this optical switch, followed by 2 polarizers, 1A and 1A prime. That's like one polarizer which goes from A to A prime and then from A prime back to A. And you did the same thing at the other end, and you have the equivalent of a polarizer which moves every 10 nanoseconds, a polarizer here which moves every 10 nanoseconds, and you'll be smiling. Well, you won't be altogether happy. Here's our polarizer. That's what it looked like. I'll tell you later on if you want to know why we decided this was better than all the heavy crystals. The experiment was pretty tough because with all the switches, it reduced the signal. Instead of doing it in 2 minutes, we needed a quarter of an hour, and a quarter of an hour, it's a lot more difficult. You need to take more measurements. The experiment has to be kept stable for hours and hours. That was a problem. We overcame that. And then I think I should also point out that we switched almost periodically. I say, well, the generators weren't stable, but still, there was a regular switching, whereas in an ideal situation, it would have been random, but that wasn't possible with our principle. We did the experiment, it existed, and it was performed by. We didn't do this for too long, but over a reasonable period of time, we found violation of Bell inequalities by past 6 standard deviations. The measurements on both sides were separated in relativistic terms. In other words, there was no possibility for the 2 sides of the setup to communicate with each other. Let's now move on to the modern generation, the terrific experiments that were carried out. What happened? Well, there were people who managed to develop sources of pairs of photons which could be fed back into optical fibers. That was the great revolution. I couldn't do that because they were emitted at a large angle and it wasn't possible to feed them in. If photons are emitted at a large angle, you can't feed them into optical fibers. Thanks to a new technology, however, it was possible to feed these photons into an optical fibers. And substantial progress was even made here with Nicolas Gisin and his co-workers. Not only were they able to feed them into optical fibers, but they developed a technique by means of which the photons could be fed into the optical fibers of Swisscom, the Swiss public telephone network operator, at night. I imagine you had to do this at night. You weren't allowed to do it during the daytime. So at night, while people weren't phoning so much or using the internet all that much, so at night, Nicolas was entitled to put his entangled photons in Cornavin, and he measured in Bellevue, and he measured in Bernay. I'm not sure what the distance is between these various points, but a couple of dozen kilometers. I said a moment ago that we were so proud to be able to say that we had entanglement over 6 meters. Well, he managed over 30 or 40 kilometers, and that's quite something. Same year, 1998, Anton Zeilinger, using optical fibers, but these were researchers' optical fibers. I'm not sure whether the Austrian telecom operator is less cooperative and less understanding than the Swiss one, but anyway, they did it in an experimental setup, and they basically repeated our experiment. In other words, they switched the orientation of the polarizers while the photons were traveling on the fibers, but they were pretty long. There was time to... They were able to randomly select the orientation of the polarizer, and they managed to establish agreement with quantum mechanics. To put it in a nutshell, or to take a little bit of a shortcut, I think we can say that there was still some imperfection. And there was the so-called sensitivity loophole. Because detectors don't detect 100% of photons, somebody who is in favor of the theory of hidden variables would say that, well, there was somebody in Boulder who used trapped ions, and his experiment was used to test entanglement with detectors or with detection methods with 100% sensitivity. These ions are 1 micron apart, so he wasn't able to test the locality side of things. But I think it's reasonable, looking at all the results achieved, it's reasonable to draw the conclusion that Bell inequalities have been violated in a highly convincing manner. And I think it's fair to say that Einstein's vision of the world, namely local realism, is untenable. We have to move away from this world view. What does this all add up to? I'm coming slowly but surely towards my conclusion. Well, Einstein himself actually had considered that one had to give up local realism. Not that he had to do so, but he argued ab absurdum. He said, if you don't agree with what I'm telling you, well, then this is what you're going to have to accept. And it was so unacceptable that he hoped to be able to prove his point. But today, with violation of Bell inequalities, we simply have to give up this theory of realism. And what we have to accept are words, Einstein's own words. We either have to drop the need for independence, we'll come back to this later on, either drop the need for independence of physical realities present in different parts of space, either you do that, or you have to accept that the measurement carried out on a first system will instantaneously, that was Einstein's word, it will instantaneously change the real situation of S2. So Einstein says, if you don't accept my worldview, then you have to accept that there is no independence between what happens here and there. And when I say here and there, I'm talking about space-time. Nothing can connect these two volumes in space-time unless it can travel faster than light. So in fact, he's saying you have to accept that there is no independence between the two sides. And if you measure here, then it will inevitably affect what happens there. This is what some people refer to as quantum non-locality. The fact you have to accept that if you absolutely want to have images, then you have to accept the idea that what you do here will affect what goes on there. Some physicists prefer to refer to quantum holism. And to use that term, holism, what does it mean? It means that it's all one entity. It means that a pair of entangled photons or particles make up a whole, and that you're not allowed to consider that it is the sum of what you have here and of what you have there. The property of the whole add up to more than the sum of the property of part 1 and part 2. The two added together. I'll come back to that in a moment because it's very important when we begin to talk about quantum computing. I'm now going to embark on the third and last part of my talk. These incredible properties of inequality have resulted in a new aspect here, which is quantum information. And as I see it, we're heading towards a new quantum revolution. What's happened is that in the early 1980s, Feynman in particular, and other physicists as well, said we're going to use these extraordinary quantum properties, entanglement. We're going to use entanglement in order to process information differently and to propagate and disseminate information differently. So there we saw the concepts of, or the ideas of quantum computing, quantum cryptography, and quantum teleportation arising. These ideas came up. Quantum entanglement is at the basis of quantum cryptography, teleportation, and computing. I'm going to give you a quick rundown on this, but my colleague tomorrow will be developing these aspects more fully. Quantum cryptography. Here we have two friends, Alice and Bob, and they want to exchange a coded message. And there's a horrible spy called Eve. Let me explain to you why Eve. Well, the Americans call people who listen at doors eavesdroppers, people who listen at the keyhole. And so they decided to call the person who's listening in, the spy, call him Eve for eavesdropping. So until not so long ago, I used for Eve a beautiful Renaissance painting of a lightly clad Eve with the serpent, and I was severely criticized, not by Calvinists, but by feminists, because I showed them this beautiful Eve. So now I've decided to illustrate Eve by using this ugly man with a horrible moustache. I mean, you know what ugly men with moustaches look like now, don't you? Well, so here we have the eavesdropper, the spy, who's bent on intercepting the message being sent by Alice to Bob or Bob to Alice. The essence of cryptography is that if there is a key, if you have a key, a random series of ones and noughts, which is the same for Alice as it is for Bob, and if Alice encodes her message using this key, Bob can decode the message using the same key, and mathematically we can prove, Shannon's theorem proved this, we can prove that it's impossible to decode the message. But there's one condition which has to be met, and that is that the key be used only one time. So Alice and Bob exchange a message. Alice says, I'll see you tomorrow, meet you tomorrow, okay, sends the message, and then she changes her mind. But she is not allowed to use the same key again. She has to have a new key. And what it boils down to is that you have to be able to give Alice and Bob identical keys, and without horrible Eve, the eavesdropper, without him being able to intercept the keys. Once the keys have been distributed, that's it. So how do you go about distributing at a distance two identical keys in a random matter and make it absolutely secure? And the answer to that is you can do it by using the laws of quantum mechanics. Arthur Eckert developed a method which uses entanglement. If you take a pair of entangled photons, it's only at the last moment that you know if you have +1 or -1 here, but then you'll know that you'll end up with the same thing at the other end. So you can't spy or intercept anything. If there was anything to intercept, then that would mean that there were some hidden variables. So provided Alice and Bob occasionally carry out the Bell inequality test, they can telephone on a normal telephone and make sure that they violated Bell inequalities. There's no hidden variable then, and if there's no hidden variable, nothing can be intercepted. It's only at the last minute you either get +1 or -1, and then you receive +1 or -1 at the other end, but that happens at the very last minute. If you have a very smart eavesdropper who really has phenomenal quantum mechanics or physics, he will intercept the photon, measure it, and send out a photon with exactly the same polarizing as the one he found. But if he does that, what will he be doing? He'll make the photon polarization real. He's creating a hidden variable. He's manufacturing one. And if you have a spy on the line doing that, since every so often Bob and Alice test violation of Bell inequality, and they will see that it's no longer being violated, and they'll therefore know that there is an eavesdropper out there. The laws of quantum physics therefore can guarantee that you cannot have any eavesdropper listening in. The distribution of the key is something which will give absolute 100% security. Quantum computing, and you'll hear more about this tomorrow because it's getting late. In a nutshell, how does the quantum computing work? It works on the basis of the idea that when you start entangling particles, you have far more information in the entangled state than you would have individually in all the individual components. In a quantum bit, which you can have at 1 or 0, or all the other intermediate states, but once these are entangled, potentially the amount of information which can be put in there is exponentially much larger than you have with conventional bits. So quantum bits carry exponentially more information. The question, therefore, is it really fair to say that we're undergoing a new quantum revolution? I believe we are, and let me explain why I am convinced of this. The first quantum revolution is the one we started in the 20th century, and it went up until 1960 or 1970, and it was based on wave-particle duality, and you heard a lot about wave-particle duality this week. Wave-particle duality was applied to large entities. In electrical current, you have millions and millions of electrons, and in light rays, you have millions and millions of photons. This wave-particle duality, as applied to large ensembles of quantum objects, has given rise to magnificent discoveries. We've been able to understand the structure of matter. It's taught us about superfluidity and superconductivity and other fantastic properties that we've been able to understand. In addition to these concepts, which are of interest to our theorists, it's also fueled a huge technological revolution. Superconductors, for example, there aren't all that many applications for the time being, but you did hear how important it is on Monday. There's something that has been far more fully developed and which is very promising. We've got lasers, transistors, integrated circuits, computers, hard disks, all of which has given birth to the Information and Communication Society and information highways. Without quantum mechanics, that would not be possible. And it's all based on what you have at the top of my slide here. Today, since the beginning of the 80s, we've become aware of the fact that entanglement brings a new dimension to quantum theory. It's a revolutionary concept, which is what Einstein and Bohr suspected. Bohr could sense that there was something underneath all this, and Schrödinger too, but it took Bell to demonstrate it. It's radically different from the wave-particle duality, and quite recently for me, maybe other very smart people understood it earlier, but quite recently only have I begun to understand that the concepts of entanglement have a lot to do with condensed matter, quantum many-body problems. We have to try and understand all the subtleties of the way in which matter conducts electrical current, and in particular the issues relating to superconductors and temperature, which you've heard a little bit about already. For some years now, people like myself come from nuclear physics and optics. Thierry Marquis, for example, organized a whole program. He is from this world. Only 10 years ago, we couldn't talk to each other. We lived in separate worlds, whereas today we understand that we're battling with very similar problems because they're all linked to entanglement. And there's another issue which I haven't developed so far, but it's implicit in many of the things that have been said this week, and that is the fact that for some decades now we've known, thanks to experiments, how to isolate individual quantum objects and to check them, to trap them. We know how to observe them. We know how to have them undergo all sorts of horrible things. And therefore, the question has arisen, how is the theoretical, how do we use the theoretical description of quantum physics? It used to apply very readily to probabilistic prediction and all the large ensembles, large objects. But when you're dealing with one single photon, for example, smaller things, we had to rethink the way in which we use quantum physics. Today we know how to describe it in theoretical terms, and we know about experiments. We can handle atoms and photons and electrons and ions, and even some of our colleagues today are able to have tiny little microcircuits which behave in a quantum manner. In other words, we go beyond natural quantum objects and are starting to be able to actually artificially create quantum objects. These ingredients together, the understanding of the importance of entanglement and the fact that we can control individual quantum objects, that adds up to a new quantum revolution. The question is it going to lead to a technological quantum revolution? There are already some signs of it. Quantum cryptography, for example, is already working. Nicolas Gisin, I think, is one of the first people who really helped to develop applications in this field. His group worked on techniques which make it possible to use ordinary fiber optic networks. Here you see a link between Geneva and Lausanne. It's used daily by some customers. I wasn't told how many customers there are. If we were in America, I'd be absolutely sure that it's the American army. But since we're in Switzerland, I'm sure it's chocolate manufacturers who are using this new link. Anyway, whatever the matter, it works. It clearly works. What about quantum computers? Well, I don't think we can buy one yet, unless, of course, Professor Blatt decides to sell a quantum computer in the near future. We'll hear what he has to say tomorrow. For the time being, quantum computing is a fascinating issue. It's a matter which basically boils down to the question as to how big an entangled quantum system can be. Is there a maximum number of microscopic objects which can be entangled? And this actually brings us back to Schrödinger's cat. The question is, can an object which is as large as a cat, for example, display these fantastic quantum properties like entanglement? In quantum physics, where we're trying to entangle larger and larger quantum objects, in conceptual terms, it's exactly the same as Schrödinger's cat and that issue. I've had problems with feminists, as I already told you, and when we're working on Schrödinger's cat, we have to be careful because you might get into trouble with the Animal Protection Society. The SPCA called on Professor Schrödinger and got angry with him because of the way he treated his cat. So we have to be very careful when talking about Schrödinger's cat. But on a more serious note, it's a highly interesting issue, and tomorrow you'll hear about this. I don't know whether Rainer Blatt will talk about Schrödinger's cat, but I'm pretty sure he's going to talk about quantum computing. Having said that, all I can say is that these are fascinating times, and I'd like to thank you all for your attention.
Voilà, merci Alain pour ce...
Thank you, Alain, for this extraordinary summary. So those who want to leave us, we'll give them time to do so. And all of those of you who want to remain with us, you can put your questions on pieces of paper and hand these over to the hostesses. And as I said, we'll try and answer a few of your questions this evening, and all the others will be answered on the website.
gezegd.
Thank you for the advertisement.
Well,
That was a tough one, a tough talk. Good one.
you think it was too difficult for the public?
Yes. We'll see how the book will go. But I think it was a nice talk for me. I really enjoyed it.
You think it was too difficult? Yes. Yes? Okay. I don't know. It depends for whom. I don't know how to present it in a simple way. If people want something simple, then I do wave particle duality for a simple thing. But if you want to speak of entanglement, I don't know how to speak. It's a very difficult issue. I don't know how to speak simpler entanglement.
So I suggest we start since we are already pretty late, so it will be 20 minutes about.
Let's talk about it later, but I
think I probably don't need this.
you get it. I think we delivered a lot.
I hope so.
No. As you well know. I'm tempted once in a while to try it, but I'm not good enough for that.
Yeah. So fascinating.
What's that?
To me, this is the biggest program.
Voilà, on en vient au la dernière.
So we still have about 20 minutes of questions and answers, and all the questions that we are unable to answer this evening, well, if you check the website, you'll find the answers on the website. You'll find the link to the website on the Right Colloquium website. Now, first question is as follows. Quantum physics. Can you, thanks to quantum physics, envisage the existence of parallel universes?
In English, the question is, does quantum physics allow one to think of parallel universes?
It's a tough one.
So, Wolfgang.
Well, in the understanding of an experimentalist, the concept of parallel universes means that if you have a particle in a quantum mechanical superposition state, it can be here or it can be there, that the possibility to detect it here and the possibility to detect it there are realized in two different worlds. And we live in one world when we detect the particle here. But there is another world, another universe, where the particle is detected over there, and those worlds exist in parallel. So every time a quantum measurement process happens, another parallel world opens up.
Yes.
So that is my understanding what the concept of parallel universes mean. As a physicist, I would say this is philosophy and not science, because the standard interpretation of quantum mechanics that I simply have a 50% probability to find the particle here, and that's what it is. That this description is indistinguishable from a description invoking parallel worlds. So for me, the concept of parallel universe is a rather strange view how you can describe what experimentalists observe, but most experimentalists prefer a description where there is only one world, namely our world.
Ok, on va pas je vais pas traduire ça, je vois que vous savez pas tous évidemment la traduction.
Johan voulait dire quelque chose. He said it so well. Okay, yes. No, he said it very well, but it should be.
Et toi, tu peux parler français. Hein.
Ah oui, pardon. Il faut dire.
You have to tell the audience that we have with us colleagues who are very respectable physicists, who are not charlatans or quacks, who think that this concept of parallel universes is the best way of representing quantum physics. I'm like Wolfgang, I'm an experimentalist. I find it very difficult to discuss matters in terms of multiple worlds, but we have respectable colleagues who believe it's the only logical way of expressing this in terms of quantum formalism. As there are none of them here this evening, we have to state, nevertheless, that they do exist and that they are very respectable indeed. Second question. Entangled states. Why isn't it possible to pass on instantaneous information? I see that people have read the slides properly. Even if there's quantum non-locality, even in the pictures of what we're showing and what we do here influences immediately what's happening on the other side. We cannot transmit the information instantaneously. I cannot resist the temptation of showing you two slides that show exactly that. The idea is follows. Arthur, so I've changed the names. Arthur has replaced Alice and Bob. This time we're talking about a man first. Arthur is going to change the orientation of his polarizer. Once the orientation has been changed, when the photon arrives here, given the description I've given you here, it seems to influence the position of the polarizer here. So Beatrice on the right-hand side, is she informed instantaneously that Arthur's changed the orientation of the polarizer? The answer is simple. If she looks here, the answer is no, because she's got a 50% chance of having minus or plus 1. Nothing has changed as far as she's concerned. But if she compares these results to the results that they get the other side, as the correlation depends on the angle of the two polarizers, she can find out that the orientation has changed. But to do that, she needs someone here to look at the results here, picks up a normal landline and rings her up and tells her the results, and the landline phone is not going to go faster than the speed of light. Sounds stupid what I've just said, but in reality quantum teleportation works exactly the same way. In quantum teleportation you've got a first phase, you have the feeling that it's taking place instantaneously, and the second phase during which you have to do something here, look at the result of the measurement, pick up your phone, and then change something at the other end, and that's the end of teleportation. So the fact that there is a quantum channel that seems to be instantaneous, but that the only operations seem to be useful and adding an additional channel, seems to be catching on, this idea. So you could say it's quantum non-locality is not that terrible, but I'd like to convince you that this is the case nevertheless, because let's say that Arthur changes these orientations and writes down all the measurement results. Beatrice changes the orientation of the polarizer, looks at the results and takes them down, and you look at the whole of the results from Beatrice and the results from Arthur, and you look at them side by side, and if you look at the results a posteriori, you see that something has really changed instantaneously. You couldn't use that straight away, but we realize that something has changed instantaneously, but it wasn't possible to use that information for practical purposes. So up to you to decide whether it's disturbing, not really disturbing, very disturbing. Be that as it may, I'd like to end by quoting a well-known physicist who asked himself, is this a real problem? Answer is, it has not yet become obvious to me that there is no real problem. I cannot define the real problem, therefore I suspect there's no real problem, but I'm not sure that there's no real problem. So that's why I'd like to investigate things further. And this sentence was written, re this problem, by Richard Feynman in the paper in which he talked about quantum computing. Talking about entanglement, Feynman wrote this sentence down. So it's up to you to decide where you want to hold on to, and I have no further slides.
Yeah, there's an intriguing aspect to it. The fact that nature doesn't allow to transport information beyond the speed of light, although the entanglement seems to work beyond the speed of light, rests on the fact that quantum mechanics is so has a probabilistic nature. So if it wasn't for this nature of quantum physics, the experiments would allow to transport information beyond the speed of light. So this probabilistic character of nature is one can put it this way, a way nature protects itself from transporting information beyond the speed of light. This is closely connected.
Okay, that's...
There are aspects which are important in that quantum statistics is different from classical statistics. But since we just talked about changes, information which we suddenly have about a remote location, let me try to give you a demonstration. I have a coin here and I share the coin with Rainer. Close your hand. And you don't know who has the coin. And now I suggest we send Rainer to the moon. I mean, I could go to the moon, but I prefer to stay here. So now assume Rainer has gone to the moon, and it takes light a second to travel to the moon. So assume Rainer is on the moon. And now I open my hand for you. Here is the coin. So we know instantaneously that Rainer doesn't have the coin, and he's on the moon. So we can predict that instantaneously. We have instantaneous information what happens on the moon and what Rainer would discover when he would open his hand. There is no contradiction that because we know the coin was either here or there, we have instantaneous information what is happening on the moon in this moment when Rainer opens his hand. But there is no way how we can send any information from the Earth to the moon by exploiting this correlation.
But you should ask that your model of the coin is a hidden variable model. Yes.
But this is a statistic. You can't explain what...
Okay, but you should say that this cannot be the explanation of violation of Bell's inequality.
No, this has nothing to do with Bell's inequality. I just wanted to demonstrate...
What you show is an example of hidden variable.
But also, exactly, the coin is a hidden variable, but yes. I simply wanted to demonstrate, and I hope the demonstration was convincing, even with Rainer staying here, that to gain instantaneous knowledge about what happens elsewhere, it is as if information flows faster than the speed of light, but this is not a contradiction, because the correlation that there's only one coin was created already earlier. It's not that this information, this correlation has moved faster than the speed of light, it's just the information, our knowledge.
Yes, but if you allow me a comment, in your example, the image I can develop doesn't imply anything going faster than light, because in my image, the coin is here, your end, or in the other end, but when you open the end, nothing happens. While on the description that I have given of the collapse of the wave packet, at the very moment when I do a measurement here, then if I insist on describing it in our space and not sticking in the Hilbert space, then apparently something changes elsewhere. So, I mean, you see.
I completely agree with Alain that this is not explaining Bell's inequality. Okay. It just demonstrates statistics and information. But the quantum mechanical case is much more surprising, yes, and much stronger.
Yes.
Yes. Okay. Donc en tout cas, on a une bonne démonstration que.
So we have a demonstration that interpreting problems lead to ongoing debates, and if David Gross was with us this evening, we'd have an even longer discussion about the matter. Next question. So quantum correlations or entanglement, can this characterize particles that don't have the same origin, of a different origin? Everybody was in agreement. Who would like to answer that one? Rainer?
Entanglement is sort of, as I will describe tomorrow night, superposition across distances, and that doesn't rely on the indistinguishability of the particle itself. It's just degrees of freedom that you have. So you could have, for instance, an atom of the species calcium and an atom of the species barium, and you really want to you want to entangle them, then this is possible. So you could have different kinds of degrees of freedom that you could entangle. And so, for example, you could entangle a degree of freedom of a particle that is an internal state of the electron being up and down or in a certain superposition, and, for instance, a motion, as we will see tomorrow. There's plenty of ideas.
Alors on continue, je pense d'ailleurs demain.
So Rainer tomorrow is going to talk to us about teleportation, and if you teleport an entangled particle, you will be able to show entanglement, though this will be demonstrated tomorrow. It's another simple question. Can you entangle several photons amongst themselves? I'm not going to ask any one of you to answer these questions. Come along tomorrow evening, you see that you can entangle all sorts of things. The second question, a specific question for Alain. According to you, what's the practical application which is the most disturbing to do with entanglement? Derived from entanglement, which is the most disturbing? Well, the quantum cryptography diagram that I showed you, the Eckert diagram, because this idea that because it happens at the very last moment, right up until the moment where you take the measurement, the result is not predetermined. I find that this is an extraordinary idea of the impossibility to spy on, because there's nothing to spy on. The quantity to spy on does not exist yet. It's only going to become created later on. I think that's fascinating. It doesn't yet exist. Everybody agrees. Good. Fantastic. I'm not going to contradict you. I'm not about to contradict you. Far from it. And a far more subtle, difficult question. We've noticed with entanglement that you can do away with this concept of space. Can we do away with the concept of time as well? Yes, to a certain extent, because one of the properties, one of the characteristics, insofar as we try and describe these phenomena in the real world, in the real space, what's remarkable is that as events are separated by the space interval in relativity terms, nothing that can connect them that would be faster than the speed of light, the concept of time no longer exists. So at will, by changing the system of reference, by moving more or less quickly from the laboratory, you can at will decide that an event takes place before another, or that an event takes place after another, and the time order is no longer absolute. So yes, the problem of quantum non-locality is involved, of course. Everybody seems to agree. Fantastic. Another question which sums up everything that's been said. Somebody who's listened very carefully to what you've said. So at the end of the day, says the question, the photons A and A1, what do they do? How did they go about their business? They obey the equations of quantum mechanics. That's what they do.
No.
Anything to add?
Photons at the end of the day serve to make a click in the detectors, or they simply die, unfortunately.
D'accord, je crois qu'on va rester avec cette question.
So I think we'll leave it at that, but I think it was a fantastic question, because those who listened at the end of the day are left with this impression. So what do they do? So of course they do what they're supposed to do according to the equations, but there's no image. But that's the result. There's no image which can be used to explain that A pushes B and then phones in to C. You can't say that, but nevertheless it exists. So that's the fantastic take-home message of this evening. And this being said, I suggest we thank our speaker, Alain Expert, once again for this presentation. Thank you, all of you. Thank you.